Hello everyone, Wes Failer here, one of the part-time scientists of course. Thanks for dropping by. Recently we gave a talk out at NVidia's GTC conference, San Jose, California. For those of you that couldn't be there, we'd like to share with you a little bit of the thinking we've been doing, a little bit of the code we've been writing, and just talk about space. So normally I'd make a joke about a sparse audience, and I'm glad it's not sparse. Tell you it'd be funnier in about 10 slides, which it will be. But since you can't see the audience, and I can't see you either, we'll just mosey right along. So our word is in order about our motivation. For me, I'm starting to work on a personal satellite about the size of a large soup can or a large energy drink. And that flies low Earth orbit, studded with sensors, flies a little ion engine, but it shares some of the same problems that we have to do for real, because we all know that's just a warm-up. Because here, for real, we're working with a part-time scientist, and here's a group of friends I dearly miss. I haven't been to Berlin in too long. These guys are down here in a basement at a restaurant. I think it was a Christmas dinner a couple years back, and this rover, well, it's Big Brother, is going to go here on the moon. And anytime you have to read the user manual for a Russian ICBM in order to know how and where to place your sensors, you know you have to start treating your sensor data special. You have to start doing something interesting with your sensor data, and you really have to be careful about what you collect, how you collect, and really get the most out of it. So etiquette demands we tell you what we're going to tell you. So I'm going to tell you that we're going to talk about the data collection pipeline. We're going to build up towards compressed sensing. We're going to get into a code for an actual couple algorithms, do a really cool magic trick when you do compression and reverse. And then, yep, there are some real world limits. You can only go so far with this. Things start to break down. We'll talk about those. And then we'll open it up for a little Q&A with a show of hands. Sorry, a little YouTube humor there, but actually extended Q&A with the comments, and we're happy to answer your questions. So the data collection pipeline, very common for us. You have the world, and the world is going to do what the world is going to do what the world is going to do. There's nothing we can do to stop it or slow it down or tell it to wait while we worry about power or buffers or anything of that sort. But the classic flow on a microprocessor system is you've got sensor, do some kind of filtering, usually for noise. I have an argument against that. Microprocessor coordinating the whole thing, a little temporary storage, a little long-term storage, communications, and the ever-present power constraints. So we sit there in this loop with a microprocessor grabbing data from the sensor, filtered data from the sensor at that, and shoving it into a buffer and RAM, typically small. Not to say PTS sensor or RAM is small, but a lot of embedded systems, pretty darn small RAM. And we do this over and over and over until we fill up our buffer, until we feel that we've sensed something meaningful about the world and its behavior. Then at some point we have to take that buffer out of our high-speed storage, because we wanted the highest speed storage we could get so we could get back to asking more questions about the world through a sensor. But we take it from the high-speed storage and we convert it over to usually a slower speed storage. I mean, if it's flash, you could be looking at page-oriented things much slower than the high-speed storage, but also a lot denser and a lot longer term. Turns out our communications really can't keep up with any of it. For instance, it's very common to have 1200 baud data command channel, as well as maybe a high-def video channel. And the high-def video is great, but it's saturated with high-def video. And your 1200 baud command channel might have to be a backup for ultra compressed thumbnail type video. So we really have to get the best out of this 1200 baud command channel in any kind of satellite or space situation in order to do the best we can, while constantly constrained with power. Small satellite I'm working on, you're looking at a half watt. A lot of the PTS stuff working on, much more professional. I think I'd safely say somewhere around the 100 watt range. I mean, a lot more power, but it's never infinite. It's never to the point where you can run all the motors at once. It's never to the point where you can do everything you want at once. So we're often making choices about when to sense the world, when to store, when to communicate. Wish list, though, when we start to look at our sensor data, is I'd like to get better interpolation between slowly collected data points like temperatures and voltages. I'd really like to get better frequency response out of like my plasma sensors or my motion sensors, things where when something happens, it happens fast and I need to know it immediately. And if I ever have to shove an HD video through a 1200 baud comm channel, I'm going to need some kind of image reconstruction. I think this is sort of the classic wish list. Feel free to add more, but this will do. This will keep you up at night pretty well. So let's set up our sample problem that we're working with. We're looking at temperature data that's collected once per second over 1 minute. So we have 60 total readings, and we don't have room to send all 60 of those readings down to Earth. So we need some kind of compression on these 60 readings. Now I want to draw your attention to a couple of things on the presentation here. So you notice it does not go to 0. And it's wobbly. Now temperatures probably don't wobble that fast in real life. There's something else going on. And I'm going to make the argument that we really don't want to throw away this wobble. You see all the leads on all these sensors act as antennas. If this sensor is wobbling, but we know temperatures can't physically change this fast in this part of the rover, then we know that something about the sensor wires is acting as an antenna to sense something else that's going on the rover. And that throwing away that wobble throws away mission data that we didn't even know we had. And I argue that's bad to throw away mission data on a high value mission to the moon or any place in space where you really can't go and make a fine-tuned adjustment and then just try it again. So our natural reaction to that data is just linear fit it. And then all I have to send is, the slope and intercept over that minute, and I'm done. You can see we can do that, and again, we lose all this extra information we have about the craft, and we get a nice mean squared error of 0.059, which isn't bad, but we're going to see if we can do better. So one thing we could do is we could take, say, a 10-to-1 compression. So 60 to 6, get 10 samples down to Earth. Actually, 6 samples down to Earth, so 10-to-1 compression. And do a, fit a polynomial, smooth polynomial to each segment in between. And so here I'm using Mathematica as an interpolate function. So it's like cubic splines on steroids. And this 10-to-1 compression, 60 to 6 compression, it's pretty bad compared to a linear fit. In fact, I don't think any of us would ever accept that as an acceptable fit for temperatures. So we say, all right, I'm just going to do a 3-to-1 compression. And what we see now is we're now on par with the linear fit, but we've preserved some of the bumps. So this is sending every third data point down to the ground, and then doing a cubic spline or anything fancier in between, as long as the derivatives match and you have nice clean slopes between the data points. So this is pretty nice. It is a better fit than linear, and it's bumpy, but our challenge is to see, can we do better and send less data? To do that, we have to understand something about sparseness. Right. So first thing you need to know about sparseness is not much. So sparseness, most things are zeros, a few things are not zero. That's sparseness. The other topic to think about is what happens when we take our data and turn it into frequency data. Here I'm using the DCT matrix simply because it's just really easy to code, very easy to test, very easy to code, and works well with the sample data I'm looking at here. But there's more you can do than just DCT. Don't get hung up on that. So when we take our time-based data and convert it to frequency with DCT, all of a sudden we notice this thing drops down to about 50% sparse. Most things in this new set of data are 0. And most of the interesting things that we actually care about are way over here on this half. In fact, there's just a few spikes that seem to carry most of the information payload. And the rest of this dribbles down. So we could say this is getting close to sparse. We've got a shot at this. And we'll come back to sparseness and why that's important in a little bit. But the key is, by converting this to a DCT-based frequency domain, and again, there's nothing magic about DCT, but converting DCT's frequency domain, we've achieved a pretty good measure of sparseness. So now put that on hold. Think about back to college. Think about linear equations. And I admit I did not necessarily pay the most attention in linear algebra in college, so I've had to do a little relearning, so pardon my vocabulary here. So the classic AX equals B, 5 variables, sampled 5 different ways, mixed 5 different ways, gives you 5 different numbers, B, and armed with that mixing, A, and the 5 B's, you can recover the 5 X's that went in. So that's pretty standard. 5 simultaneous equations for 5 variables, 5 answers. Okay. Well, one thing you can do is you can create an under-constrained linear system. Same thing, AX equals B, but the sizes are different. If A is as long as X is tall, but B isn't as tall as X is tall, say that 5 times. Actually, you only have to say it 3. It's another joke. You end up with a form of compression. It's a lossy compression. You know, 5 variables go in, 3 variables come out. But here is the basis for at least some kind of compression. So what good does this do us? It turns out that if you know that the X variables, if you know that these X's are mostly sparse, you don't know which ones are 0. You don't have to know that ahead of time. You don't have to assume this one is 0 and this one is 0. It's not like that. But if you know that most of these are zeros, then this under-constrained system can be solved pretty reliably. So one thing we can do is we can plug this into a least squares curve fit. And so what we're doing here, and this is Mathematica terminology, so what we're doing is subject to AX equals B for this under-constrained system, solve that, in which case you end up with a lot of different X's that could fit the bill for this equation, and choose the one that gives you the smallest, least square DCT spectrum. So any candidate X solution, take the DCT matrix of it to produce a spectrum, which is now sparse, and now take the square of that, so your normal Euclidean square, Euclidean norm, and find the vector of X's that has the smallest squared norm, and say that's the X that we will choose to satisfy this equation. So now we see that the linear, that's our baseline. That's our nice linear, ultimately perfectly filtered thing. Polynomial wasn't bad, knee-jerk reaction. But we see if we do this least squares sparse recovery, we find that we can actually get a better 3-to-1 compression, even a better 10-to-1. Our 10-to-1 compression actually does better than the linear. Anything does better than polynomial at 10-to-1. But we can start to do really good here. So we get 10-to-1 compression and beat the linear, which is good. I mean, that's outstanding, but there's more we can do. To move to the next step, to get the next best results, we have to understand that there are other kinds of norms we can work with. We've worked with the squared norm, the Euclidean distance, square root of x squared plus y squared plus z squared. There's the L1 norm, which is the sum of the absolute values. And then we have the L0 norm, which is simply the number of non-zero items. In truth, L0 is the definition of sparse. So we have some examples for what these are. So, you know, you've got a sequence such as 0057, then what you end up with is the L2 is, you know, an 8.6, but 12 is just 5 plus 7. I mean, that's the L1 norm, and your L0 norm is 2, because 2 of them have values. So we can see the differences and these different ways of thinking about the norm of a vector. Now truly, L0 norm is the definition of sparse. You want the simplest spectrum, that is the L0 norm, the simplest spectrum that has data consistent with what you've collected. The AX equals B, B being what you've collected, A is how you've mixed it. We want the simplest spectrum we can get. However, that's a combinatorial nightmare. I mean, it's one of those NP hard problems that's, you know, we're not going to solve the heat death of the universe in a general case. We might come up with some special cases, which is snazzy, but the general case is going to elude us. So, turns out the L1 norm, that sum of absolute values, is close enough most of the time to solve this system. You know, this is where compressed sensing comes from. So a few years ago, some really smart people thinking about really high dimensions in space figured out that the L1 norm results in nearly the same solution, or as the L0 norm, most of the time, as long as your mixing matrix A is specially formed. You have a certain special level of sparseness. You can't be too unsparse. And the more data, the better. So the worse the problem to solve, the easier it is to solve when you think about it this way. However, we can't go with your grandfather's L squared solver that he used on the old moon missions. This is a new moon mission. This is a new space age. We have new solvers. And I got to tell you, these things need massive concurrency, especially because we're looking at really high dimensions. And that's where the whole GPU thing came in, which is why this talk itself was presented in NVIDIA's GPU conference. How much better? Stunning. So again, we're solving a similar problem. So we are saying we've collected data B, we've mixed it A, created this under-constrained system. So there's a lot of x's that fit. So take the x's for any candidate, give me the spectrum of it, and now give me the sum of absolute values of that spectrum and minimize it. So minimize the L1 norm of the sparsified version of x, and that's the version of x that you use as our final solution. And we plug that in. 3-to-1 compression starts to look pretty good. Even 10-to-1 compression starts to look really good. We've really reduced our error rates at 10-to-1 compared to an L squared. So we've preserved the bumpiness of the signal, drastically preserved it, but still achieved a 10-to-1 compression ratio, which is highly desirable. So that brings us to our definition of compressed sensing. The recovery of non-sparse data from compressed to sparse intermediate data representation. General cycle, create it, compress it, recover it, and then bring it back to real. Now, I want to talk to people, because about half the people at this point that I've ever talked to are sitting there in the back of their heads going, wavelets, hasn't this guy ever heard of wavelets? My God, hasn't he heard of wavelets? Of course I've heard of wavelets. I've looked at JPEGs on the internet. How can you not hear of wavelets? Wavelets make things sparse. They're really good at making things sparse. Just more code than I had available to me at the time. Sparse data can be compressed. Wavelets alone, though, are not the compression. Wavelets work for compression because they help you decide which coefficients to just throw away. Compressed sensing doesn't throw it away, it instead mixes those coefficients together in order to preserve the information. whereas other techniques that use wavelets take that same sparse wavelet structure and they record the peaks, where the peaks of the wavelets were. And so they record an index and a wavelet value and then discard the rest. So that is a form of compression, but it's not a form of mixing. So wavelets alone are not compression. Compressed sensing needs something to sparsify data like a wavelet or DCT or an FFT or a million other sparsifiers. In fact, there's a whole branch that goes out and tries to find sparsifiers that are specific, highly specific to your likely data. So if you've already had a moon mission and you get hold of some of the data, you can come up with a sparsifier that works well for moon mission temperatures and likely to give you really good compression with your data. And then if you haven't, then you take something a little more general purpose. Maybe we use wavelets, maybe we use DCT, etc. Anyway, I just wanted people to get that out of their head and know that yes, I've heard of wavelets and you're fine. You use it anywhere in here. We've been using DCT, but wavelets alone are not compression. Think of compressed sensing as mixing the wavelet coefficients, like mixing the DCT coefficients together rather than discarding them and then recover from that mix. So we've achieved some better interpolation by minimizing the L1 norm of the sparse version of X. What did we do on the remote system? We applied some kind of mixing matrix to our collected data. Now that could be bits, could be zeros or ones, plus or minus ones. Those could be ints, they could be floats. But likely our communication packet was not changed. We didn't communicate any more data than we would have had we done, say, the polynomial, where we had sent every third or every 10th data signal. We would have, again, I'm rejecting the linear one because it didn't capture the bumps that were mission critical. So we didn't change our comm packet, but we now have suddenly a lot more data being recovered on the ground system because we're applying the sparsifier on the ground. So notice that the remote system did not sparsify. The remote system did not multiply by the DCT matrix. It was not actually necessary. The remote system just had to apply this A matrix, which should be stored as very compactly as a series of bits. So that's pretty nice. Communication didn't get bigger. The math didn't get too much more complicated. Didn't need floating point on the embedded system, and we got a lot better error rate. So that's pretty good. Now it turns out you can go a little farther. You can start to combine steps. So we take this AX equals B, which we can only really solve if we know, in an under-constrained system, if we know the X. So if we say, we know that if you take the DCT matrix times the sparse version of X, XS, that will give us X. So now we can substitute that in, and razzle-dazzle, we end up with, you take this matrix, A dot D, which is matrix multiplication of your mixing matrix times your sparsifying matrix times the sparse data, gives you the data that you actually send down to the world. And then you minimize the L1 norm of that sparse data subject to ADS equals B. And then once you've found the sparse data, then you do like we did at the beginning. Just multiply by the DCT matrix to get back to the unsparse data. This is the common form of it. Most solvers work this way. They give you sparse data solution, which means they're expecting a matrix as input that is a combination sparsifier and mixer. So that's what we have to deal with, some kind of way to combine those. First algorithm we want to look at is called the matching pursuit algorithm, and I'll show you just how simple this little algorithm is. It's just that simple. Okay, I wish you could see me giggle at this one. It's not a resolution thing. I personally am a computer programmer. I dabble with the math. I'm getting better every day, and I have a lot of smart people being very patient and trying to teach me, and I'm grateful for that. but I still have a lot of trouble reading some of the notation on here. Still require an interpreter. And I'll tell you, this is the clearest description of matching pursuit I've found so far. And even this doesn't quite match some of the code implementations I've seen. So matching pursuit's a little bit of a mystery to me in terms of how this notation directly relates. But it is out there, and I bring it up because it's a challenge if you're a computer programmer and you're trying to take this notation and produce code for other people on your team. And it's also a challenge if you're a mathematician writing these notes, trying to talk to a computer programmer who says, where's the for loop? I just want the for loop. Where is that in here? There's a language barrier, and it is a challenge present in the compressed sensing community that is still being addressed. However, I ran across a really great paper from M. Undercut, and very grateful. These researchers published code for CPU and GPU. They used CUDA for NVidia. They used cuBLAS, and so I started with their code. This really got me thinking, hey, this is possible. This is doable. So I started with their code, converted it to use the thrust library, which you see down here in our prototype. Our device vector, host vector, that's thrust. NVIDIA distributes the thrust open source project as part of CUDA. So made this work with thrust. Undid a few optimizations they did because they didn't want to store matrices as transpose, because it was just a mind twist to be constantly switching those indices around. See, I can't even say it straight, so you can see what a problem that is. So this is the start of the matching pursuit algorithm. Intentionally kept it away from too much object orientation. Made it so we have nice flat vectors. So this is a 2D array of columns by rows, but it's been flattened, and there's a little function that will tell you the Fortran style indexing required by cuBLAS. So not C style, but Fortran style column major indexing. So matching pursuit starts with a residual. This is your guess about how far off from the actual answer you really are. And the key is that its length, dictionary columns, doesn't match the first piece of data you're shoving into it, compressed signal, which is a little shorter. It's actually only dictionary rows long. That's a subtlety I think is lost on some non-programmers. So be proud of yourself if you caught that one. So here we assign residual to dictionary columns of zeros, but then fill it with this smaller data, which we know does not release the allocation on the extra data, merely just fills the first lump of it with compressed signal. And then there's an empirical bit here about how many iterations you should go before you give up. Be careful of making this too big, because life doesn't get much better if you increase it. And then residual error. Because you're going from sparse back to real data, this is not necessarily residual error on the real data. So experiment a little and set it where you think works well with your application. So we use a lot of cuBLAS in here, which this is one of my first experiences with cuBLAS, and I must say quite enjoying it. So this gives us the L2 norm of a vector. So that's the initial norm, and then we use that to compute how far we've gone. And this is the guts of matching pursuit. It says, while we still have some work to do and we haven't run out of tries, then do a big old matrix multiply of our matrix or dictionary transposed with the compressed signal, put it into the residual, find the biggest item in the residual, pull it out, do a little manipulation there to update our data, update our answer based on that. A little multiply to apply or update back into our estimate, and then see how close we've gotten with another norm 2, and then increment and repeat. That is matching pursuit. A little more scaffolding code around it, but the guts of that, admittedly hard to read for me as a non-mathematician, hard to read blob formulas is fairly straightforward code. And don't let all the parentheses and commas fool you. I mean, they're just casts. There's relatively little data movement going on in here. So I need a few other little routines to make this friendly to use. You remember I told you this is stored Fortran style. So we use this little macro here. What row, what column, and how many rows are in your matrix to give you an index. Compressed sensing needs plus and minus ones a lot. Coin flips. 50-50 coin flips. Not plus 1, 0, or minus 1. Just plus or minus 1 coin flips. So we use sign quite a bit. And then the math to get a single cell in a DCT matrix is pretty straightforward here. So you could fill a whole matrix, admittedly with some overhead, but you could fill a whole matrix with this function. Now, I want to draw your attention to, notice that I didn't use N or M or any other of the common linear algebra abbreviations up here, like with the IDs. And that's very important. You don't do that because the literature is inconsistent. Some will use N for rows, some will use it for columns in their matrices. Some will flip back and forth depending on it. And then some code, depending on where they're at in the paper, which author was in the paper. And some algorithms are inconsistent with other algorithms, so just spell it out, row, column, don't go with N or M. When you're writing test cases, make random data. Create a random sparse signal, minus, 0, plus. Create a random dictionary, that's your coin toss, plus, minus. And create sample data from those two. Call your algorithm, check the results, see what happened. So I can't tell you the importance of having unit tests here, obviously. You know, you need to have some test cases that you know what they should come out. You can verify that you've plugged it in because it's maybe real data you're really interested in. But you should also have some random data. And make a random data, run it through the algorithm, see how it reconstructs, and then see how well the answer came out. Because that random data will test more cases than your imagination will find. So let it run there. Do some random data. Run maybe 500 random runs and see what the bounds on the errors were. That's going to be very useful to you in double checking how your algorithm is running. Can't stress the importance of random inputs enough here. So matching pursuit's been pretty good at exploring around, except the iteration count goes up drastically as you start adding variables. But when you've got small problem sizes, so low dimension space, matching pursuit's been good to me. And it's also been good when the data is not really sparse. Let's say, you know, most things are close to 0, they're like 0.1 or 0.2, and the things I care about are a 1 or 2 or 5. So imperfect sparseness, a little DC offset or something like that. Matching pursuit's been pretty good about that. It doesn't seem to take more iterations, and it doesn't seem to change the answers it gives. So I've been pretty pleased with that. Now, to move forward, you've got to learn how to do the L0 calculations with Thrust. Thrust is the C++ template library that's open sourced, and NVidia redistributes it as part of CUDA. So, really cool thing with Thrust is you write these functors. So basically a structure that's got an operator, essentially just a parentheses operator, and you call their really snazzy little transform reduce, which will go through every item in this array, this whole X array from begin to end, call this function, this transform, this non-zero count functor transform, and add up all of it together. So here's you're telling it to add it together, that's a transform. You're telling it to reduce by plussing or adding. So tell me if it's 1 or 0, if it's non-zero, and then add up all the non-zeros. That's transform reduce, that gets run on a GPU, it's very fast. It would also work on a CPU if you want to just play around with some of this stuff at home. However, you'll need to change this from device vector to host vector. Now we're ready to look at a really cool algorithm. This is called AMP, or I think it's an approximate message passing algorithm. It's one of those little predictive algorithms. It's just this simple. Seriously, I must admit, I found this a lot easier to read than the matching pursuit algorithm description, and I'll tell you why. See right over here, t greater than equal to 0, equal greater than equal to 0. That's our iterator. So this is an iteration that starts at 0 and then counts up. Already home ground for us C++ programmers. And then there's an implied order to all these things. So my residual equals the signal we got minus my mixing matrix times my best guess plus some weighted function times the residual from the prior iteration. The next guess is equal to this function of the current guess plus the transpose of the mix times the residual for the current residual. And then this really weird thing. I don't use semicolons to pass parameters, but it seems to be common in the mathematical notation. So it's all parameterized by this parameter theta t. But it turns out, this b that's referenced up here in the r, okay, that's doable. M is a known equation. That's one of the sizes of the arrays. This is the L0 norm of our current guess, x, which makes sense because we want to factor in, we're trying to get a smaller and smaller guess, simpler and simpler guess. The theta t parameter is got the square root of the L2 norm of the residual, easy to get, CUDA. Again, m is a constant based on our problem dimension. And a, well, that's been empirically determined in the literature for us. There's a very common set point value to converge pretty quickly. And this n function is a soft thresholding, which we can see is basically a little if-else-if. So this translates to code pretty straightforward. So I was quite pleased with that. I could get my mind around the iterations. So the AMP function that we wrote, and we'll be open sourcing it, the AMP function that we wrote takes actually the same signature as the matching pursuit. Same parameters, same order, everything, so that you could swap one algorithm out for the other and compare it. It's pretty straightforward. There's, of course, a little setup. The same kind of thing we had to do for matching pursuit. How many iterations are we willing to accept? What's our acceptable error? Notice we dialed that down. It was 1e minus 7 for matching pursuit. We dialed it down because even though it took a few extra iterations, it gave me about 3 times less absolute error. And that seemed worth it because this was already pretty fast. But that was empirically determined. It's the phrase, your mileage may vary, and I don't know how that translates. So we have a few constants, we have a few variables, then we get to the main loop. The main loop's in 2 chunks. Sorry, I couldn't squeeze it on one slide. So there's the update the residual chunk. It says if it's the first residual, it's a special case. Our error is the compressed signal. That's when you go through all the math and cancel everything out. Just residual is compressed signal the first time around. And then pretty straightforward from there. We've got the L0 norm we called. There's the thrust transform, and there's a matrix multiply. So pretty straightforward to get our residual. And then to update the x, we just tick through the various equations we saw there. Obviously with a few real-world variables tossed in. I also highly recommend you put comments in, what is the equation this next line of code does. Not everybody remembers CUBLAS D gem V. T is the transpose matrix multiplication. So it's helpful to have those little reminders in there in case you don't deal with this every day. I will say on a space mission you wear a lot of hats, and not all of them involve multiplying matrices, so it's good to leave yourself some breadcrumbs. And then don't forget, at the end of the algorithm you get sparse data, and we got to give it back. And then we have to do that little end function, that clipping functor, which is, like we just said, a series of ifs, else, ifs. So pretty darn straightforward. Little speed optimization of doing this negative theta variable rather than calculating it on the fly. So iterations increase really, really slowly with AMP. Really pleased. I mean, from hundreds and hundreds with matching pursuit to dozens with AMP, and roughly comparable calculation size, time per iteration. However, when the problems got small, it really didn't work well. When I started talking about 50 to 100 variables, I've not had good results with AMP yet. Likewise, with a little DC offset in there, AMP has not been my go-to. However, when AMP does work well, so we start increasing the variables count size, say maybe like 2,000 variables, not only is it faster, I get a lot better fit than matching pursuit. And not just from the 3 times. I mean, it seems to really home in a lot better. So now, a magic trick. We're going to start with uncompressed, uniformly sampled data. This is, remember, what we would normally get out of the data buffering processor, microprocessor. And we need to get the data between those data points. It's very common these days to need to get the derivatives at data points. Anybody familiar maybe with some of the work Cornell's doing, where they have their Eureka solver, their genetic programming solver, discover laws of nature by looking at the data. And part of its work is to look at the derivative estimates at the data points. So the better we can provide that, the better the algorithms can do to come up with real equations to fit the data we're looking at. And 2 ways we can do. We can take our compressed data, B, so that's our collected data that we came out, and we say that that data is actually the result of some sparse data that has been sampled and mixed. So this is the data we got. We theorize that it was mixed together and sparsified. And so we have to make a theory about how this was mixed. Now, for our purposes for testing, this is a DCT matrix, and A is a mixing matrix that provides an under-constrained linear system. Turns out, if we say every data point is actually a mix of 3 data points in our mixing matrix, this works out very well in the studies I've done empirical. So this is a 2-to-1 expansion. We take every data point, and I wish to create a new data point between each one. So a 2 times data expansion, and we do this 3-point mixing model, where I say a data point is a 3-point average, 67.5% of the data before it, 25% of itself, and a little bit about something that comes later in the future, which from an instantaneous transmission standpoint we never have, but because we're working with buffered data, we do have some knowledge about what happens in the future. Obviously a little special case at the end. So every row in here is one piece of data we collect. So this is the buffer we've received, and we're just saying, no, the real data is interconnected. Now also I will tell you, you see this structure here, where one row overlaps the other. We've got a lot of zeros, but there's a little overlap, a little stair-step type thing here. This has worked very well, because it means if you come up with a wild guess for one of these variables, that wild guess still influences everything else. So it takes out some of the wildness from a variable. Likewise, you never want all zeros in any column here. If you put all zeros in one of these columns, you're saying there's a variable here that doesn't matter. Guess anything, it's irrelevant. And that tends to go really wrong. So best to put in a really tiny correlation, you know, 1/100th of a millionth of a percent than a zero. So the wild guess there at least gets tamped down and made more consistent with the rest of the numbers. So empirically, 3-point mixing model has worked very well. So here we take a look at our world data. Normally this is hidden from us. We can't actually ever really tell what's going on in the world without actually looking at it through a sensor. Sensors always have some kind of limitation. So this is something we can never truly see. You can debate the philosophy of that. But what we can do is we can run simulated tests to say if this was the nature of the world, would our sensors give us an accurate depiction of this if this were the world? And then we can try a lot of different world estimates in order to make sure that the sensor we produce and the algorithms chain that's part of that would accurately reproduce the world so that we have a better chance of seeing the world for what it is. So here we have a high frequency signal overlaid top of several frequencies combined. Not the cleanest signal, not the ugliest signal. So now we start sampling this hidden data, and it's not obviously as clean as that hidden data was. You know, we've got a lot of these little valleys, these little dips, these little extended valleys, and you know, some real gaps in here where nothing's happening. So, you know, to our fuzzy logic human minds, yeah, there's something going on there, but that's going to be pretty hard to pick out accurate derivatives and to really see what's going on. You know, the low frequency stuff I think we all pretty well grok. But the higher frequency, again, is where the unexpected mission data lays, and that's where we want to be prepared to get that data, because that's the value. If we already knew it was up there, we wouldn't be exploring. So we need to be able to capture unexpected things and be ready to deal with that. So one thing we can do is take all those sampled data and just do a linear interpolation between each piece of sampled data, and we start to do that and it looks nicer. And I will say that, you know, we probably don't do, you know, cubic spline interpolations for tens of thousands of data points. It's just computationally burdensome. So we tend to do a lot of linear interpolations in practice. I'm not saying it's for the best, but it does happen in practice a lot. And you can see it does clean it up, and you know, it takes out some of that, but it's not necessarily a best signal, and maybe the solution is to put in some kind of filter and just get rid of that noise entirely. You see me grinning again. There's another YouTube joke, because again, we don't want to filter out all that value. So now we take our compressed sensing in reverse, where we say, no, that sample data has been 3-point mixed from some larger hidden piece of data, and I want to reconstruct that under that mixing hypothesis and to produce this sample data, this expanded sample data, and boom, now this looks really, really, really close to the data that we had in the hidden model. This is definitely preserved the spikes better, it's preserved the integrity of the high frequency noise, it's pieced it together a whole lot better. And this didn't happen just because I cherry picked this for display. It happens quite often in experimentation. The real tell how well it does versus a linear interpolation between points is look at our mean squared error. So the linear interpolation has these beats where it's bad, and then it gets pretty good, then it's bad, then it gets pretty good. And then the expanded interpolation, so the compressed sensing in reverse, way down here, so much less error for just by using the compressed sensing in reverse to expand. And what's really cool is we don't have to change anything. Nothing changed on the remote system. We didn't have to mix or sparsify anything. We didn't have to change the comp packets. We just changed how we analyze things on the ground by shoving a GPU in there to do these things in real time. And all of a sudden, boom, much, much, much better quality data coming out of the system. Alright, there are some limits. We have to deal with some limits. We have to learn with them. So your dictionary, your mixing, sparsifying thing crammed together, your dictionary must follow the restricted isometry condition. So there's been several papers I've been reading about this. Some say that the elements of that array need to be very random, need to be drawn from a Gaussian distribution, basically coin toss divided by the square root of the number of samples you want to keep. Others say just grab n random rows from the otherwise square Fourier or DCT matrix. Others say almost any matrix will do, so knock yourself out. Personally, I've either had really bad luck or that's not true. So I'm sticking with the Gaussian with the coin toss, or the random rows from like DCT or Fourier. No zero columns, and personal experience is have overlaps, small overlaps, so keep the sanity flowing. So if you find a good sane suggestion for one number, that sanity flows through to the other numbers. It seems to be a lot better quality, even if it's a small interconnect. Now, there is a phase transition where things go from good to bad. So, up here, bad. Down here, good. Wish I had a green laser pointer I could show you. So down here, very good. The key is to look at your transmit to read. So if I read a bunch of data and I want to compress it down to this transmit, what's my ratio? So if I want to get down to a 50% transmission ratio, then I got to look over here. How sparse is the underlying signal compared to how much you transmitted? So we take 1,000 readings, transmit 250 of those. So we're over here at 0.25. And of those 250 transmitted numbers, there are really 125 non-zero spikes in the spectrum, or whatever basis we use, DCT, wavelet, whatever. So that's a 0.5 ratio there. We're clearly into the unsafe region where we have extremely low probability of recovering the original signal. This is a game, and there's a little gamble here. So that doesn't work out too well. So you've got to. However, if the signal is 25 sparse, then we're well into the safe range. In fact, we have room for a slightly worse signal, slightly noisier signal, and be okay. The key about how okay depends on these two lines. So this nice blue line here, positive negative, says what are you trying to recover? You're trying to recover positive and negative numbers, then your limit's a little worse. If you're trying to recover only positive numbers, in other words, you had a spectrum, but everything in the spectrum was positive for some reason, you could guarantee that, then you could have a slightly worse, slightly worse signal here. But for a lot of what I ended up doing with the DCT work, things never come out just positive. They're positive and negative. So we're down here with a few more restrictions. In fact, for our earlier example, where we had a 3-to-1, we're doing pretty good. I mean, this is where the actual data is looking at the formulas. So the key is when you do any kind of planning, that you're going to end up, say, you've got some data point here, and you'd like to make the transmit packet smaller. So that's sliding to the left. However, since you're making the transmit packet smaller, you're increasing the sparseness to transmit ratio. So every move you make to condense your transmission is moving you straight up into the danger zone. So you want to watch out for that. Now also, we had to do a little magic trick earlier, a little sleight of hand, because this is back to our temperature data, which again does not go to 0 and is bouncy. And we had to do some preconditioning on that to up our sparsity. So the spectrum data on here looks pretty good, right? One giant spike, a little bit of a rebound, and then, boy, the rest of that might as well just be 0, right? That looks pretty sparse. However, not so good recovery, 0.041, and 10 to 1, 3 to 1, and 10 to 1, just terrible recovery using that data straight up. However, if we applied that linear fit, take that linear line and subtract it from take the linear prediction, subtract it from every point, we end up with something that looks very like a spectrum, which is very friendly to the DCT signal itself. Many thanks to a guy named Manny at GTC for pointing out that correlation and really highlighting it. He had some good insights there. So wish that you guys could have joined us at GTC. There was a lot of good discussion on this there. I wasn't the only one on compressed sensing too, by the way. So it was not a sparse conversation. So anyway, when we do that, we end up with a much cleaner spectrum that has a few more spikes, but it turns out this one compresses better. This one gives us much more better reconstruction. I think it's because when you have that one big spike, that its data doesn't get smeared out across a lot of entries. So the information from it, so to speak, doesn't flow far in the matrices. So you can see we get really good reconstructions with this preconditioned data. 3 to 1 and 10 to 1. They preserve a lot of the spikes. They crawl into the nooks and crannies pretty well. Obviously the 3 to 1 crawls in a lot better in the nooks and crannies. So a few tips for winding down here is isolate your algorithms. Don't mix sample data with actual algorithms. Make sure your buffers are pretty well isolated. Minimize your clutter. Minimize it everywhere. The algorithms are hard to see. They're going to be hard to repair, hard to fix, hard to document, hard to expand. For the love of God, do not use N, M, and K variable names. And comment things out, because everything in your life does not revolve around CUDA. At least not mine. Make sure you do a lot of unit tests and integrate visualization into your testing process. Just looking at a bunch of numbers really doesn't help you debug anything. You need to see some charts and graphs. In my case, I made sure I dumped everything out to a CSV file, and then would just double click the CSV and pull up an Excel file that I had written. And then do everything you can to feed the sparsity. Precondition or find a good sparsifier that's happy with your data that can really simplify it. Things will be a lot better for you. Future work is working on our image reconstruction. So microprocessors, small microprocessors, read as ones that are radiation and power resist, radiation, temperature, and got the right power requirements for space. These things often don't have enough memory for an entire image. They have to deal with a pixel stream coming off the camera, a line at a time. So how are these things supposed to do a very large image compression when they can't hold the image in place? In fact, they don't even have the memory for a true dictionary, a large square matrix dictionary. So instead they have to use, say, like a pseudo random number generator and generate it. So a little state machine to generate numbers from the dictionary as they go. And then likewise you have the notion of scene templates with your images. So let's say you've got a satellite and you're taking a picture of the part-time scientist's lander as it's departing low Earth orbit, breaking for the moon. Something I think would be terribly cool. Get a shot of that from a satellite we jettison. And there's some things you can expect to see in that scene. Hopefully there's a little shot of the moon. Definitely better be a shot of the lander, and be nice to have the horizon of the Earth somewhere in there just to set the stage. So if you use some kind of like Huff transform or something like that to identify where these blobs are, you could say I'm only going to be interested in pixels that are in those blobs. So that's a scene template where you translate, here are the actors, and don't care about the other pixels. So the question is, should you do that reconstruction with all the other pixels forced to 0, or should you only reconstruct the pixels in the middle and don't care about those other variables? And I leave that to people to debate, and I'll leave it to me to experiment at some point. But to me it seems like it's like playing games on that recovery phase diagram. About reducing the number of pixels could push you one way, but forcing a lot of zeros could push you another desirable way at the expense of increased solver time. Again, GPUs will help with that, so I'm not too worried about the solver time. Okay, final conclusions. Use thrust. Man, that just cuts down the clutter in your code like nobody's business. You don't need a lot of code to write a sparse solver. Sparse code, sparse solver. Didn't have to write any CUDA kernels to get into this, which was pretty nice. Code size, performance, no longer barriers. This work runs readily on a new laptop. And we're going to open source all this code. So stay tuned, check back with part-time scientists. You know, we'll get that open sourced. And I'd like to thank you and take questions from guy in the front. Oh wait, we're out of time. So just leave your questions in writing and we'll talk to you later. Thank you.